Oh damn.
Hey, what's up, my ducklings? It is I, Rick Stevenson, aka Rick, but you may call me Cool Kid Rick for short. And today, we're going to discuss the kinematic equations. In front of you, to your left, you will see the four main kinematic equations. Now, you may also see them written as the kinematic equations on the right. They're both the exact same equations, just written in different ways. Now, if using the second ones are commonly called Suvat equations. Suvat being each one of the variables that you see in the equations. So what are these variables? Well, let's look at them. S, or as you may see them on the left, the left hand equations up here, is just the displacement. U, or V naught, or V sub 0, equals the initial velocity. V, which is the same in both equations, is just final velocity, or you may also see it as v final or v sub f. A is just acceleration and t is time. Now, I'm going to walk you through a step-by-step derivation of all these kinematic equations, first using algebra and then using calculus. Is final velocity is equal to initial velocity plus acceleration times time. So how can we approach it? The acceleration of an object is determined by delta v over t. Now, this is the same thing as the final velocity minus the initial velocity divided by time. If we rearrange this equation, you can get acceleration times time is equal to final velocity minus initial velocity, and rearrange this again to find final velocity is equal to the initial velocity plus acceleration times time. Now, you can also find this through calculus. Acceleration, as I've defined it here, is the change in velocity divided by time. Now, as the acceleration, as the time interval gets infinitely small, your acceleration can be defined by dv dt. So, just move the dt, multiply both sides by dt, and you get the acceleration is acceleration times dt is equal to dv. Now, integrate both sides and you get the integral of the acceleration with respect to time is equal to the integral of 1 with respect to velocity. Now, for the limits of integration, for the, let's say, t equals 0 to some given time, and velocity, the limits of integration for the velocity will be some initial velocity to some final velocity. Now, if we integrate this, you'll get a t equals the change in velocity vf, or just v, minus v initial. And this is the exact same as what we got up here. It's the exact same as what we got up here. So just rearrange this equation and you got v equals initial velocity plus acceleration times time. So now that we know how to derive the first equation, let's skip the second equation and move on to the third equation, because we're going to need this equation to derive the other two. Now, this equation basically derives of the average velocity formula. Now, if you don't know what that is, the average velocity, that's v average, it is equal to the total displacement over the total time. And so you can rearrange this equation to get that the displacement is equal to the average velocity times the time. Now the average velocity will just be the sum of the velocities divided by the number of velocities that you have. So delta x is equal to the final velocity, or just v, plus the initial velocity divided by 2, because that's the average, and multiplied by time. And there we have it, the third equation. Now there isn't a proper method to do it through calculus as far as I'm aware, but one method of trying to get it is by drawing up a graph of what average velocity might look like. Now first, the velocity graph might be anything, so it can be some crazy graph like that. But what you need to focus on, since we're dealing with average velocity, we're only going to be looking at the total distance over the total time. So that's just gonna be a straight line. We're just focusing on the straight line. We're ignoring all the curves, though it may be there. This line will determine the average. So if you focus on just the average, so velocity time, straight graph, and you want to find the area under the curve. Now that'll give you displacement. So the integral of the velocity with respect to time is equal to the displacement. Now we don't actually need to solve or evaluate this integral. We can just take the area of this triangle, since it's a pretty basic shape. Now that's just half base. Now what's the base? That's the time. So half time, and what's the height? The height will be whatever your initial velocity is over here, your initial velocity on the y-axis, and whatever your final velocity is up here. So it'll just be the sum of your initial velocity plus your final velocity, and hence we get equation: the displacement is equal to initial velocity plus final velocity divided by 2 times time. And it's the exact same as the other equation we got. Now that we know how to get the third equation, we can go back to the second equation. Now this is the second equation, and I want you to focus on the two equations that we've already derived. I've got them up here. And now to solve this, to get this algebraically, let's substitute the first equation in the third equation. Now what happens when you do that? You get delta x is equal to the initial velocity plus initial velocity plus the acceleration times time divided by 2 time the whole thing times time. So what happens when you expand this? Well, you get 2 times the initial velocity plus initial velocity times time plus the acceleration times time squared divided by 2. Now this is very similar to the actual equation. All you have to do is distribute the half across both. So the 2 cancels out here and you get a half over here, and hence you get the displacement is equal to initial velocity times time plus half times acceleration times time squared. And that's your equation solved algebraically. Now with calculus, let's start off with the equation velocity is equal to the displacement over time. Now, what happens as your time interval gets infinitely small? You get your instantaneous velocity, which is the velocity at one very specific point in time, as dx dt. Now, same thing as before, the velocity times dt is equal to dx, and take the integral on both sides. The integral of velocity dt is equal to the integral dx. Now, the limits for these integrals, let's do the integral for the velocity for some initial time, so time from 0 to some given time, and the limits for your displacement to be some initial displacement to some final displacement. Now, before we solve the integral, let's substitute the value for v. Let's substitute equation 1 for v. So what you get is the integral from t equals 0 to a given t value for the initial velocity plus acceleration times time dt, and that is equal to the integral from initial position to final position dx. Now, when you solve this, take the integral of both sides, you get the initial velocity times time plus the acceleration times time squared. You add 1 to the exponent, divide by 2, and that is equal to some final position minus some initial position, which is just delta x. And hence, you get the same equation, delta x is equal to the initial velocity times time plus half acceleration times time squared. So the fourth and final equation, this one, to derive this, we're going to use both the first and third equations like in the previous one. Now, as you might have realized, the fourth equation has no time variable. So, what you can do to eliminate a time variable in these two equations is rearrange the third equation to find time and substitute it in the first equation. So if you rearrange the third equation to find time, you will get 2 times displacement divided by the sum of the velocities, or just v rather. Now substitute that in the first equation. Initial velocity is equal to final velocity is equal to initial velocity plus acceleration times, substitute this here, 2 times displacement divided by initial velocity plus final velocity. Now, when we open up these brackets, we get final velocity is equal to, let's first open up with acceleration, 2 times acceleration times displacement, and let's get a common denominator of initial velocity plus final velocity. By getting a common denominator, we have to multiply the final velocity plus initial velocity times the initial velocity expression. So what we get is initial velocity times final velocity plus initial velocity squared. Now multiply both sides by initial velocity plus final velocity, so you get another denominator, and what you get on the left hand side is initial velocity times final velocity plus final velocity squared, and that equals the initial velocity squared plus final velocity times initial velocity plus 2 times the acceleration times displacement. Now the final velocity times initial velocities cancel out, and what you're left with is final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. And there we have solved for the equation using algebra. Now, to solve using calculus, we can use the previous two expressions that we got for the previous equations. Acceleration is equal to dv dt, and velocity is equal to dx dt. Since we're trying to get at a time, let's solve for dt on both equations and equate them to each other. So what we get is dt is equal to dv over a, and dt is also equal to dx over v. So equate them to each other and we get v dv. Let me write that neatly. V dv is equal to a dx. Now let's take the integral of both sides. So the integral of velocity with respect to velocity is equal to the integral of acceleration with respect to the change in position. So for the limits of integration, we're going to have the limits for the velocity as some initial velocity to some final velocity. And for the acceleration, we're going to have some initial position to some final position. Now, the integral, when we evaluate the integral of velocity with respect to velocity, we get the velocity squared divided by 2. And then we substitute the values of the limits and we get half final velocity squared minus the initial velocity squared. And that equals the evaluated integral over here, which is just the acceleration times the final position minus the initial position, which is just displacement. So what you get is the final velocity squared minus initial velocity squared is equal to 2 times acceleration times displacement, and hence final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. And we have solved for all 4 kinematic equations using algebra and calculus. Now, if you are a little confused on the integration parts, I've got a video that explains the basics of integrations and what basically integration is. So check that out if you want to know what it is. Anyways, see you later.